Okay, next let's consider another assumption that might make our training or transfer learning more efficient. And this is an assumption that is relevant to many real-world applications, is that we can also now pick or have some knowledge, specifically observe the state space of at the target domain, of our target domain, what we are actually trying to solve. Okay, so previously, up to now, we discussed pure zero-shot transfer, where we learn in some source domain, we train on this, and then we proceed to the unknown target domain, but we never take a step backwards, right? So once we transfer from our train policy to the target domain, that's it, we can't go back. If we don't know anything about the target domain, that's probably the best we can do. Well, we just try to be as robust as possible, right? High entropy and high domain randomization. But what if we are able to see a few images from the target domain? How can we use that knowledge? Any idea? Any suggestion?
Not sure.
Maybe you can try and use that to improve your... Oh, we still, by the way, okay, I didn't say that. We still assume that we can play with the source domain. Okay, so let's say still training the source domain is in simulation, so we can play with different things there, the environment. But now we have we're able to observe some states from the target domain. What can we do?
Train on those as well?
I'm not sure that we can train because we don't know the model, right? We can't progress there, but we can use those and tell our source domain, the one that we used to train on, hey, try to be similar to my target domain, as similar as possible. Try to resemble that, or try to be indistinguishable. Right? And indeed, this is something that generative adversarial neural networks can help us a lot with, where so a quick background for GANs, generative adversarial neural networks. These are generative models where we train both a generator and a discriminator. The generator is trying to generate samples from some target domain, maybe images, or maybe a state space that we're really trying to fit as closely as possible. And we also train a discriminator that is in charge of identifying the counterfeited samples, the counterfeited, let's say, states, or maybe images if you're generating images. Originally it's from, it was used or demonstrated on images, right?
Yes.
Okay, so we train a discriminator using fake samples, maybe from our simulation environment, and real-world samples that we obtain from the real world, right? We assume to be able to obtain some samples from the real world, and we train our discriminator to, well, identify which of the states came from the real world and which came from the simulation environment. Then what we do, and this is generally in GANs, we take the derivative of the discriminator, so we generate states from our simulated environments, and then hopefully, or not hopefully, our discriminator, if it's very good, it will identify that these are not real-world samples, but they come from our simulated environment. But then we can take the derivative of these samples with respect to the input. Sorry, the derivative of the fakeness of the fake score, right? If the fake score was very high, we'll say, okay, what's the derivative? How can we change the input? How can we change the image such that this score will be reduced, that the discriminator will have a harder time identify that these are fake samples. They come from our simulation environment. We'll take these derivatives and train our simulation environment to produce those states that seems or that look more like the real world, right? Or samples that can help us fool the discriminator in some sense, such that the discriminator will not be able to identify whether these samples are coming from simulation or from the real world. How do we get there? By training our simulation to be very good, right? To produce samples that look like the environment. If you didn't understand the generative adversarial training procedure, don't worry too much about it, but you can read about that. I just described it in a very high level. Just know about this tool that can be very useful if in your domain of choice, the one that you're trying to train off, you do have some samples from the real world. Question, yeah?
So these GANs mainly help the simulation states look similar to real world states, but they do not model like the real world dynamics in any way, right?
So no, you can use them also to, so the discriminator can be, you can train it to discriminate whatever you want. You can also discriminate it to, train it to identify transitions. And then not only will you require it for the states to be the same, but you also require the dynamics to be the same. It depends what you have from the real world. If you have examples of also the transitions, use that, sure. Why not? You'll train a better simulation model, right? Okay, so let's see an example of that, of this approach.
In this work, we extensively evaluated the effect of using simulation and domain adaptation on vision-based robotic grasping with a total of more than 25,000 physical test grasps on a set of 36 diverse objects unseen during training. Our proposed approach takes as input synthetic images generated by our simulator and produces adapted images that look similar to real-world ones. We then train a deep vision-based grasping network with adapted and real images, which we further refine with feature-level domain adaptation. We show that by using synthetic data and domain adaptation, we are able to reduce the number of real-world samples needed to achieve a given level of performance by up to 50 times using only procedurally generated objects in simulation. Our method does not require paired examples and can perform well even in the absence of labeled real-world samples.
All right. So let's just summarize the forward transfer approaches that we observed. First of all, we saw how we can just perform pre-training and fine-tuning. We saw that standard fine-tuning with reinforcement learning can be inefficient. Sometimes it is, but in many cases it's not. Maximum entropy formulation can help, and progressive networks can further help provide us with more efficient transfer learning. How can we modify? Then we added the assumption that we can somehow modify the source domain. So how can we do it to obtain better transfer? We saw that randomization can help a lot. The more diverse we are on the source task, on the training task, the better it is for transferring the knowledge to the new task. How can we use a modest amount of target domain data? So next we added the assumption that we can pick or we can see some of the states. As I said, we can also use transition maybe to train on transitions from the real world. How can we use that data coming from the target task? We can do domain adaptation or fine-tune our domain in simulation, our source task, to make a network, a discriminator, unable to distinguish observations from the two domains, from simulation or source task and our target task. What we're trying to do is to modify the source domain observations to look like the target domain, and then of course our training becomes more efficient because, well, our source and target domains are similar, more similar. So some extra reading. This, specifically if you are looking to implement one of these algorithms, because you have a relevant domain, and that might be the case, this is As we said previously, these techniques are very important if you're trying to train robots in the real world. So here you have several papers that were just used throughout this the slide deck so far that you should further examine.